What this says is that one of the 6 roots of I, geometrically, is what? It's that complex number which is 1 unit from the origin. That means it's on the circle of radius 1, centered at the origin. And the angle must be 15 degrees. The argument is 15 degrees. And by the way, just to check this out, that this really is, that 1 comma pi over 12 really is an answer here. How do you raise a complex number to a power if we view it as a length? To raise this to the 6th power, we must raise 1 to the 6th power. That will still be 1, so I'm still going to be on the circle. When I multiply, I add angles, so when I raise this to the 6th power, I'm taking what? 15 degrees 6 times is 90 degrees, and that puts me right up where I is supposed to be. In other words, to do this thing backwards, so to speak, I know that 6 times the angle I'm looking for must be 90, so the angle itself must be 15. For example, if I was looking for the 8th root of I would do what? I would know that when I add the angle to itself 8 times, I want 90, so the angle would have had to been 90 over 8. And again, I leave this for you as exercises. The point is that geometrically, the 6 roots of I are all equally spaced points. The first one is the point 1 comma pi over 12, and the rest are spaced equally along the circle at 60-degree intervals. You see, it breaks the circle up into 6 equal parts. I come back to here. Notice that, for example, if I take this one, which is 75 degrees, if I take 75 degrees 6 times, notice that I come back, what? 75 times 6 is 450. It means I go all the way around and come back to I when I raise this to the 6th power. To help you see this geometrically, I'll pick, of these 6, one of these happens to be very easy, at least to me. 9 pi over 12 is 3 pi over 4, which happens to be 135 degrees. And 1 comma 3 pi over 4 is cosine 3 pi over 4 plus I sine 3 pi over 4. The cosine of 3 pi over 4 is minus 1 over square root of 2. The sine is plus 1 over square root of 2. So in typical x plus iy form, one of the roots is 1 over the square root of 2 times minus 1 plus I. In other words, the real part of this complex number is minus 1 over the square root of 2. The imaginary part is 1 over the square root of 2. And I leave it again as a voluntary exercise for you to do, to actually raise this to the 6th power and find, amazingly enough, that you do get 1 for an answer, I for an answer. Now, you see, I just picked one particular example, but this would have worked for any roots that I wanted to extract, and this is very important from a mathematical point of view. The complex numbers are closed with respect to extracting roots, and let me summarize that for part of today's lesson over here. The idea is that one of the reasons that we had to invent the fractions after we knew the integers was the fact that the integers were not closed with respect to division, that the quotient of 2 integers didn't have to be an integer. One of the reasons that we had to invent the complex numbers after we had the real numbers was that the real numbers were not closed with respect to extracting roots. What I've just shown you in terms of a particular example is that the complex numbers are closed with respect to extracting roots. This means that, in particular, the basic operations that are involved in solving polynomial equations. In other words, what do you have to do to solve a polynomial equation? Nothing more than the basic operations of adding, subtracting, multiplying, dividing, raising to powers, and extracting roots. All of these operations are closed with respect to the complex numbers. And what this means is, if you wanted to write a polynomial equation which had complex numbers as coefficients, you would not have to invent any more complex numbers. You would not have to invent a new number system to solve this equation. Namely, any polynomial with complex coefficients has complex roots. And I think that's enough for today. I want you to drill now on the exercises. Next time, we will talk about functions using complex numbers. At any rate, until next time, goodbye.